When you imagine the future of clean energy, what's the sound you hear in your head? Probably a silent, electric hum, right? Well, what if I told you the future sounds less like a whisper and a lot more like a roar? We're about to dive into a powerful, familiar piece of tech that's making a comeback nobody saw coming. Yeah, let's be real. When someone says hydrogen power, your brain probably jumps straight to this, a fuel cell. It's the technology we've all heard about for years. It quietly turns hydrogen gas into electricity, and the only thing that comes out the tailpipe is water. It's the clean, silent, futuristic dream we've all been sold.
But what if there's another way? One that's a lot more familiar, more robust, and has kind of been hiding in plain sight. What if you could take that exact same hydrogen and just, burn it inside a roaring, good old-fashioned internal combustion engine?
And that's what we're talking about today. This is hydrogen's other power source, the comeback of the hydrogen internal combustion engine, or H2ICE as you'll see it called, and its totally unexpected role in our push for a zero-carbon world.
So you gotta ask, right? For years, fuel cells got all the hype, all the research money. Why the sudden comeback for the good old combustion engine? Well, the thing that changed the game wasn't some flashy new invention from a lab. Nope. It was regulation, paperwork.
So yeah, why now? The answer isn't buried in some complex engineering blueprint. It's actually hidden in a really clever bit of legal language. This is the story of how a regulatory loophole is kicking off a revolution for what they're calling the zero-emission engine.
Okay, so here's the backstory. It all kicks off when the European Union decided to get really serious about cutting CO2 from heavy-duty vehicles. And we're talking about the real workhorses of our economy. Long-haul trucks, giant construction equipment. These things are a nightmare to electrify with just batteries. They're too heavy and need to go too far.
So to push for new solutions, the EU created incentives for companies building zero-emission vehicles, or ZEVs. And here's the twist, the part buried in the fine print. The legal definition of a ZEV actually allows for an internal combustion engine, just as long as its CO2 emissions are crazy low, below 1 gram per kilowatt hour. And that right there, that was the opening H2ICE needed.
I mean, the proposed rule basically spelled it right out. It said, look, if a fuel has zero carbon in it, like pure hydrogen does, then its CO2 emissions are, legally speaking, zero. And just like that, burning hydrogen in an engine meant it qualified as a ZEV. This was huge. It unlocked these super valuable credits for manufacturers and kicked off an absolute frenzy of new development.
But okay, just because it was legal didn't mean it was easy. To make this comeback a reality, engineers had to wrestle with the unique nature of hydrogen itself. As a fuel, it's got some incredible superpowers and some pretty serious kryptonite.
This really gets to the central paradox of hydrogen. If you measure it by weight, by the kilogram, it's a superfuel. I mean, it packs almost 3 times the energy of gasoline. Amazing, right? But if you measure it by volume, by the liter, it's got almost nothing. Because it's such a light gas, it takes up a ton of space, and trying to cram enough of it onto a truck is the #1 challenge.
Then there's its flammability. Gasoline is kind of picky. It only wants to burn in a very narrow window of air and fuel. Hydrogen? It's not picky at all. It will happily ignite if it's just 4% of the mix, all the way up to 75%. Now, for an engineer, this is an incredible tool. It lets you run the engine incredibly lean and cool in ways that are just impossible with any other fuel.
But, of course, there's a catch. That same burn anywhere quality has a big downside. It takes practically nothing to set hydrogen off. 10 times less energy than gasoline needs. This means a tiny static spark, or even just a hot spot on a valve inside the engine, could ignite it when you don't want it to. Preventing stuff like backfire becomes a very real, very serious engineering problem.
So let's just lay it out. You've got this fuel that's incredibly powerful, but a huge pain to store, and it's easy to burn, maybe a little too easy to burn. All of this creates this central conflict, the main dilemma for any engineer trying to build a modern hydrogen engine. And here it is, the great trade-off between power and purity. If you run the engine hot and fast to squeeze out maximum power, those high temperatures cook the nitrogen and oxygen in the air together, creating polluting NOx emissions. But if you run it super lean and cool to get rid of that NOx, your power just falls off a cliff. For a long, long time, it seemed like an unbreakable compromise. You had to choose one or the other.
But this is where modern technology finally breaks the stalemate. New tech, especially super advanced fuel injection and exhaust treatments, has given engineers two new paths forward. Two ways to solve the dilemma and finally get the best of both worlds: clean and powerful.
Okay, so step one was just solving the raw power problem. See, in older hydrogen engine designs, they would mix the hydrogen gas with air before it all went into the cylinder. And because that hydrogen gas takes up so much physical space, it would crowd out the air the engine needed to breathe. It was essentially choking the engine and limiting its power. The solution was a total game changer. It was a fundamental shift from that old method, port fuel injection, to a new one, direct injection. It's all about timing. Now they let the cylinder fill up completely with dense air, shut the valve, and then inject the hydrogen directly inside. No more air getting displaced. And the results are just staggering. Compared to a regular gasoline engine, that old port-injected hydrogen engine really struggled, maybe making 86% of the power. But a modern direct-injected one, it can unleash over 120% of the power of a gasoline engine. Suddenly, the power problem wasn't just solved, it was obliterated.
So with the power issue finally off the table, engineers could focus on emissions, and they came up with two clear strategies. Think of it as burn lean versus burn and clean. The first path, burn lean, uses that massive flammability range. You just run the engine with so much extra air that the fire itself stays too cool for NOx to even form. The second path, burn and clean, runs the engine hot for maximum power, which does create NOx, but then you use an advanced exhaust system, just like on a modern diesel, to scrub it clean before it goes out the pipe.
Okay, so the engineers are cracking the code. The challenges are being solved one by one, which brings us to the big question. Where does this technology actually fit in our future? Let's talk about the hydrogen engine's sweet spot.
Right off the bat, this tech isn't for your daily commuter car. Its sweet spot is in the absolute toughest, heavy-duty jobs you can imagine. We're talking long-haul trucks, massive construction, and farm equipment. Things that demand high, continuous power all day, every day, in really rough, dirty environments. Plus, there's a huge practical advantage. These engines get rid of waste heat way more easily than fuel cells, which need enormous, bulky radiators that are a nightmare to package on big machines.
And this might be the most surprising finding of all. We're all conditioned to think of fuel cells as the absolute peak of efficiency. But the analysis shows that for these specific, high-load, heavy-duty jobs, there is a crossover point where a hydrogen combustion engine can actually be equally or even more efficient than a complete fuel cell system. That's a huge revelation. So to wrap this all up, this isn't about the hydrogen engine replacing every battery or every fuel cell out there. It's about a robust, familiar technology finding a new purpose, a targeted solution for some of the toughest jobs in decarbonization. And it leaves us with this one really provocative question. Could the familiar roar of an engine, powered by the universe's lightest element, actually be the sound of a cleaner future?